Hello, I'm Trevor. I run the Chem 2 AEWs here on campus, and today I'll be talking about molecular geometry, electronegativity, and intermolecular forces. We'll look at a few example molecules to examine these concepts. The first is water. Let's examine the geometry. Water has two lone pairs on the oxygen. So if these lone pairs repel each other, and these pairs of electrons repel each other, well, they're all negatively charged, so they're all going to repel. The shape that's formed between these hydrogens and the oxygen is going to be bent. So this is a tetrahedral configuration with four is tetra, but only two of them are substituents, the other two are lone pairs, so we call this bent. Now let's talk about the electronegativity. The oxygen is the more electronegative element here, so a greater amount of the electron density in these hydrogen-oxygen bonds will be nearer to the oxygen. And we indicate that with these arrows here. So what type of intermolecular forces can go on with water? We'll start with the most basic ones. London dispersion essentially occurs in anything that has an electron cloud, because you can always induce a dipole in an electron cloud. Anything that is polarizable can have an induced dipole. So almost every molecule is going to have London dispersion. Here we also have dipole-dipole. Because the oxygen is going to be partially negatively charged, and that's going to leave a partially positively charged region towards the hydrogens. So we have a dipole on the water. We're going to get dipole-dipole interactions where when water interacts with other waters, the negative of the oxygen is going to be attracted to the positive of the hydrogens on an adjacent molecule. And finally, we're going to have hydrogen bonding occurring. Hydrogen bonding occurs when you have a hydrogen bonded to, covalently bonded to a very electronegative element like oxygen or fluorine. And you have lone pairs in order to receive those hydrogen bonds. Essentially what's happening is the hydrogens on this water molecule are exchanging very, very rapidly with the hydrogens on all of the other water molecules. And that creates a very strong intermolecular force. The next example we'll look at is carbon dioxide. Now, here, if we start with the geometry again, carbon only has two substituents attached to it. So this is going to be a linear arrangement. There are no lone pairs. So if this region of electron density and this region of electron density wish to repel each other as much as they can, they'll be 180 degrees apart. Be completely linear. The electronegativity rules still apply. Oxygen is more electronegative. If we go up and to the right on the periodic table, where fluorine is the most electronegative, oxygen is very close, more so than carbon. And so we do get these partial negative regions and partial positive region. But the question to ask is, do we get dipole-dipole interactions? Is this molecule a dipole? No. The symmetry of these oxygens actually cancels that out. So we don't see dipole-dipole interactions with CO2. We do see London dispersion. As we discussed, anything with an electron cloud can be polarized. And we do have some hydrogen bonding occurring. You might think that's odd, there's no hydrogens in here, but there are lone pairs on these oxygens. So those lone pairs on those oxygens could interact with a hydrogen bonded to an electronegative element, like in water, for example. You can see this occurring in soda, where you have CO2 dissolved in water. You have interactions between the water and the CO2 that keep the CO2 in solution. And so we have, this is a hydrogen bond receiver, as it's called. The last molecule I'd like to look at is, we'll do sulfur tetrafluoride. Where I use this hash and wedge notation to indicate three-dimensional structure. The hash is going into the board and the wedge is coming out of the board. So here, sulfur has 2 lone pairs and 4 substituents, so it's in the octahedral configuration. It has 6 electron pairs attached to it. So if they all repel each other, you get an octahedron, but only 4 of those 6 have something attached to them. So you're going to have this interesting arrangement that we call seesaw. This is named after the playground equipment, because if you were to look at this and imagine it sitting flat on the ground here, you could rock it back and forth and it looks kind of like a seesaw. So what interactions do we have going on here? Well, fluorine is more electronegative than sulfur. So we're going to have dipole-dipole interactions because we have negatively charged region and a more positively charged region. And the negatively charged region does not cancel out due to symmetry. So we have dipole-dipole. And we also have London dispersion. For more information, you can come to my workshops on Wednesdays from 6 to 7 p.m. or my office hours 2 to 4 p.m. Mondays and Wednesdays.